Hi, my name is Malte Renken and I'm presenting also on behalf of my co-authors Arnaud Casteigts, Mikhail Raskin and Viktor Zamaraev our paper called Sharp Thresholds in Random Simple Temporal Graphs. First of all, I need to tell you what temporal graphs are. So here's a graph on 4 vertices, and what makes it temporal is that we allow the edges of this graph to change over time. So we have a number of discrete time steps, at each of which the edges of the graph may look differently. Notice, however, that the vertices are not subject to change. They stay constant throughout the entire lifetime. We can represent this temporal graph in a more compact format by first drawing what we call the footprint. This is the graph of all edges appearing at any point in time, and then labeling each of these edges with the times at which it appears. For example, this diagonal edge appears only at time 4. In this talk, we focus on the case where each edge appears only a single time, and furthermore, at each time, only one edge is present. We call these temporal graphs simple temporal graphs. Furthermore, we only care about the order of time labels, but not about their actual values. And the reason we're interested in the order of time labels is that we want to study properties related to temporal connectivity. Temporal connectivity is built upon the notion of a temporal path. A temporal path being just a path in the footprint along which the edge labels increase. So in this case, the path runs from S to T and has labels 1, 7, 9. Notice that temporal paths are inherently directed. The motivation for studying temporal paths is that many processes, for example, a disease spread in this graph, would occur naturally along these temporal paths. We call a vertex a source vertex if it can reach all the other vertices of the graph using temporal paths. In this case, the center vertex S is a temporal source because it can clearly reach A, B, and D directly, and it can reach C and E via vertex D, and it can reach T using a temporal path I just showed you a moment ago. We call a vertex a sinc vertex if it can itself be reached by every other vertex in the temporal graph. Of course, sinc and source are symmetrical concepts if we reverse the direction of time. In this graph, T would be an example sinc vertex. If every vertex can reach every other vertex, then we call the graph temporally connected. Of course, this is equivalent to every vertex being a sinc vertex or every vertex being a source vertex. This example graph is not temporally connected. For example, there's no temporal path from T back to S. If a graph is temporally connected, then we call a subgraph which preserves this connectivity property a temporal spanner. Temporal spanners are analogous concepts to spanning trees in normal graphs. However, in temporal graphs, a tree is not enough to get temporal connectivity. In fact, it has been known for quite some while that you need at least 2n-4 edges for a temporally connected graph, even if you're allowed to pick these edges yourself and label them as you like. More recently, Casteigts and FOCS showed that there are even temporal graphs on a quadratic number of edges where removing any edge would destroy temporal connectivity. When we started working on this, our question was, which of these scenarios is actually the likely one? So, in other words, if we take a random temporal graph, does it fall more into the first or into the second category? Of course, to ask this question, one first needs to state what a random temporal graph even is supposed to be. And we chose to work with a very basic model, starting with an Erdős-Rényi random normal graph. So just a graph on n vertices where each edge appears independently of all the others with probability p. And then we order these edges randomly. And the result we call a random simple temporal graph, and we denote it by a fancy G, index np. However, it turns out that there's a slightly different but equivalent definition, which is more convenient to work with, where we again start with an arbitrary random graph and then label each of these edges independently of all the others using a random time label from the real interval 0 to 1. This guarantees that we have unique labels, and we can also now label all edges independently of each other. Furthermore, this allows us to study a random growth process. So here we take the random simple temporal graph with edge probability 1, meaning it's just a complete graph where every edge is labeled with a random time label between 0 and 1. And then we take the temporal subgraph from time 0 to time p. So we stop this growth process at time p. Then the result will be a model for the GNP random simple temporal graph. So let's do a short experiment. Here are 100 vertices, and we will now simulate this random growth process. I have colored the topmost vertex red, and we can think of this vertex as being infected and track the spread of the infection during this growth process. So let's start by adding some edges. And as you can see, at this point we have had a first edge connecting to our red vertex, and this allowed the infection to spread to a second vertex. So let's continue. In the beginning, only a few red edges appear, but over time, as we pick up more and more red vertices, the speed at which red edges occur will increase and increase until we have reached a large number of vertices. So at this point, we have now reached most of the other vertices, but there are still a couple white vertices remaining. And now the spreading begins to slow down again because it takes a lot of time for these vertices to receive edges by which they will also become infected. So there's still one white vertex on the right side. And now we got all of them at around 450 edges. Notice that this is still only a rather small fraction of all the possible edges. So back to my slides. Here I've drawn a timeline of GNP ranging from 0, meaning no edges, to 1, meaning all the edges. And I've already mapped out two well-known events here. The first one at 1 over n is when the footprint, remember this is the graph where we ignore all the time information, starts to have a giant component. And the second time log n over n is when the footprint becomes connected in the non-temporal sense. And log n over n is also when we proved that the first temporal event we're interested in occurs, which is that most vertex pairs are able to reach each other through temporal paths. So in the simulation we just did, this would be the time where our randomly chosen top vertex was able to reach almost all, but not quite all, of the other vertices. The second event is the point we stopped the simulation at. This is when most vertices become source vertices. So this was the time when our top vertex was able to reach all the other vertices. And in fact, this is also the time where the very first temporal source appears. So if we had started with a different vertex and not a top vertex, there would have been little to no chance of becoming a temporal source before time 2 log n over n. And of course, both of these, for symmetry reasons, are as well true for sinks. So this is also the point in time when most vertices become sink vertices. And using that, we can already derive a result about temporal connectivity, which is the following. If we wait until time 2 log n over n, then most vertices will be sink vertices. So all the vertices will be able to reach one arbitrarily chosen pivot vertex. And then we wait 2 log n over n more time for this vertex to become a source vertex again. And then all the vertices will be able to reach all other vertices through this single pivot vertex, and the resulting graph consisting of the tree from everybody to this pivot vertex and subsequently from the pivot vertex to everybody. So it's a union of two trees of 2n minus 2 edges overall. is what we call a pivotal spanner. In particular, this shows that at time 4 log n over n, the temporal graph is already connected. But in fact, we were able to prove that this happens already much earlier, at time 3 log n over n to be precise. So this is the first time when all vertices are able to reach all the other vertices. Now you might ask, at time 3 log n over n, how many edges do I need to get a temporal spanner at this point? So we know at time 4 log n over n we can get one with 2n minus 2 edges. We know that the absolute minimum possible is 2n minus 4. So how small can we get at time 3 log n over n? And the answer is pretty small. In fact, we were able to prove that at time 3 log n over n, so at the very first time the graph even becomes temporally connected, there already exists a spanner of nearly optimal size that is 2n plus small O of n many edges. But if you require it to be absolutely minimal, then we conjecture that you need to wait until time 4 log n over n, at which time we were able to prove that an optimal spanner occurs, and we conjecture that it does not appear any earlier. So all of these events I've drawn here, except of course for the conjectured one, we prove to be sharp thresholds, which means that the probability that these events happen more than an epsilon factor away from the point in time I've drawn them at vanishes as the size of the graph increases. So I want to try to give you a little bit of intuition for some of the proof ideas, and for this I need one more concept, which is that of foremost trees. So first of all, again, I have a temporal path here from vertex S to vertex T, but there's another temporal path from S to T here, which is this one, and this one has the property that it has the earliest possible arrival time at which S can reach T, which is 8. And we call such a path, which arrives at the earliest possible time, a foremost path. And a nice property about these foremost paths is that for any chosen root vertex S, we can arrange all of them in a tree, what we call a foremost tree. So this is a tree in which all the foremost paths from S to all the vertices which S can reach are arranged. And to build this tree, we can use a very simple algorithm. Works a little bit like Prim's spanning tree algorithm. And it works as follows. We start with just the vertex S at time 0, and then we run time forward. And whenever an edge appears, which we like, which means an edge which increases the size of our foremost tree, then we add it to our tree. So here at time 1, we add the edge from S to D. And at time 2, we add to C. At time 3, the edge between A and B is not connected to our tree, so we ignore it and we will never add it to our tree. Instead, at time 4 and 5, we add more edges. At time 6, this edge would close a cycle, so we're also not interested and ignore it. Time 7, another edge, and at time 8, our temporal tree is complete, and S has now been able to reach all other vertices through this temporal tree. Now I want you to imagine that we have taken a complete simple random temporal graph, meaning all the edges appear with probability 1 and each of them receives a random time label. And you pick your favorite root vertex S and start growing a foremost tree using the algorithm we just showed. And then you will notice that if at some point your tree already contains k vertices, for the next step, there are k times n minus k potential edges that will help you grow your tree. Which means that the growth of your tree is fastest when you have around half of the edges already reached. And here I've graphed this more precisely. And in fact, it turns out that the growth of this temporal foremost tree follows this logistic growth curve, where at time log n over n, we reach around half of the vertices. And at time 2 log n over n, we reach finally all of the vertices. And from this, we can motivate why log n over n is a sharp threshold for vertex S being able to reach almost all the other vertices, because for large graphs, this curve becomes so steep that a tiny amount of time after log n over n, we will be already up here, having reached almost all of the other vertices. But for the final last couple vertices, we will need to wait another log n over n until time 2 log n over n. So I've said a lot about simple temporal graphs. Let me also say a couple words about non-simple temporal graphs. We also looked at a model for non-simple temporal graphs in our paper, where we said that each edge appears independently according to a Poisson process, which means that each edge independently of all the others can appear between 0 and a large number of times, where the expected number of occurrels is exactly p. Note that p can now also be chosen to be larger than 1. For example, here I've sampled H5 1.2 graph, meaning we have 5 vertices and each edge appears on average 1.2 times. Notice that, of course, some of the edges appear more than that and some don't appear at all. So the nice thing about this non-simple temporal graph model HMP is that we could easily show that all our threshold results hold as well for HNP. So basically the same proofs work without modification, or even simpler also for HNP. In fact, it's more difficult to do the proofs for the simple temporal graphs, because in this non-simple model you have more independence between past and future, whereas in the simple temporal graph model it gets a little bit more technical. This brings me to the end. So in summary, we show in our paper that the following are sharp thresholds for both simple and non-simple random temporal graphs. At time log n over n, an arbitrary vertex pair will become connected. At time 2 log n over n, the first temporal source will appear, and also already almost all of the vertices will become sources. At time 3 log n over n, all the vertices will become sources, meaning that the graph is now temporally connected. And at this moment, we already get a spanning temporal subgraph with only 2n plus smaller of n edges. And at time 4 log n over n, finally, you will get a pivotal spanner, which means there's a single pivot vertex for which all the vertices can reach all the other vertices. And we conjecture that this is also the time at which you can first get the absolutely optimal spanner with 2n minus 4 edges. Thank you for your attention.